So in this video I want to explain how Quicksort works. So Quicksort is a sorting algorithm that is very efficient and it's very often used to sort arrays because of its efficiency. And the idea of Quicksort is as follows. So it picks an element somehow, and it's called pivot, and so for obvious reasons I abbreviate this with P, and compared to all other we compare all other elements against this P. So what we get is that some elements are less than P and some elements are greater than P. Yeah, and it's clear if you want to sort an array that we want to copy all those elements which are less than P. They should go to the left somehow, and elements which are greater than P, they should go to the right somehow. Yeah, so and we usually should end up with a situation that we put the P, the pivot just between those sets. So we have one set here, elements which are less or equal than P, and elements which are greater or equal than P that are here, and in between we have this pivot. Yeah, and that's the idea of Quicksort. And so then we have, if we have achieved this situation by some steps, then we're happy, because then we have clarified a lot of properties and relations between those elements. And if we do this idea recursively to this part here and afterwards to this part here, then we sort the array, because if you look at this situation, it's clear that the pivot P now has its final position. So if we achieve this situation, we have clarified the final position of this element here. And if we do this job recursively, we will clarify all positions of the elements here, and so the same holds for the part on the right. So that's the idea of Quicksort. So let's see how it works. So we have this array. Again, we have something that is of size 15, so 15 elements. And when we call this sorting algorithm, what we do first is we make a shuffle. That's quite interesting. So now we make a random shuffle, so all elements have got more or less at random place now. Why the heck do we do this? And the answer is quite simple. We want to ensure that the previous ordering is more or less random, and the reason for this is that the choice of the pivot is very, very important. If we go back to the slide again, just imagine that we choose for unfortunately something that is the smallest value or the largest value. What we end up would be that one of those sets is empty. So this is the worst situation for Quicksort. The best situation for Quicksort is that both parts that are the result of this separation algorithm, procedure here, is that these parts are more or less of equal size. It doesn't matter if this one is 2 or 3 elements larger than that one, but as long as they are more or less of equal size, then it's fine. And to ensure this, we have to have something that is somewhere in the middle. And that's the reason why we do the shuffle, because if we have the shuffle, then we ensure that that we have a random distribution or random ordering anyway. And now there is no pre-ordering or whatever. Yeah, so if we now pick an arbitrary element from here, then we can be sure that it is very likely to be somewhere in the middle. Yeah, although it's clear that there is a certain probability that you catch something that is the minimum or the maximum, but this happens with a very small probability, and Quicksort can live with that. Yeah, so but as long as in the average we have something that is more or less in the middle. So now, after the shuffle, we do the sort. We call the sort method that says, okay, sort this array from the 0th position to the length -1 position. So we call this sort method here with 2 indices L and R, and they determine the end of the borders of the array that we have to sort. Now we make it single step. We are now dealing with that. And you see we have two frames here. So the big yellow frame is the part of the array that we have to consider, and this poor small frame here is just always contains just one element, and that's the pivot. We always will compare the rest of the array now with this value. So the position r determines the index of the pivot, and now we will see how we manage that to solve this array somehow, or to make some progress. So first we check whether L and R have a certain distance. If they haven't, then there's nothing to sort. Yeah, it's the same observation as for a merge dot. If the array has only size 1 or 0, then there's nothing to sort. Okay, so now we do the following step. It's called the partition method here, and we hand over the array and L and R, so the size of the array to consider, or the parts of the array to consider. And now we have to deal with the partition algorithm. What does it do? So I will just do some steps here, and then we see what happens. So we define some indices I and j, and if we then we enter the loop. So this is the inner loop of this partition algorithm, and what you see is this horizontal yellow bar. It's as high as the pivot is. So that's the point. Yeah, so we compare all those elements in this yellow frame against the pivot value, and some of them are less and some of them are greater. Yeah, and the idea is that everything which is less will go to the left direction, and everything that is greater will go to the right part of this frame. Yeah, and that's and to make this more as efficient as possible, we have two indices, namely I and j. And I is the one that is looking for someone who's greater and shall go into that direction. And j is just the opposite. It goes in the other direction. It looks for something, or an element that is less than this yellow horizontal bar here. Yeah, so and this should be copied to this or swapped to the beginning of the array. So that's the whole idea. So in the first step we adjust a and j to the initial values that we should look at. So I is now looking for something which is greater than the pivot. So we do a compare with this element and the pivot. So this is the reason why we have this comparison here. While less a of I with a of r. So we compare the ith element with the rth element. And if this is less, which it is, and we haven't reached the border, then we increase I. So we just move the I and go on. So this is not greater than the pivot, but this one is. So now what we will see what happens now. We will do the compare, and I has seen that this is greater. So so the search for for something that should be swapped to the end of the array is over. Now we are looking for something which is less than the pivot and should be swapped to the beginning of the array. So now j is walking, so to say. So this is greater than the pivot, that's fine. So a of r is less than a of j, so we decrease the j. This condition here checks that we don't run out of bounds. Yeah, so okay, we decrease j. Now we compare this element with the pivot element. Again, it's greater, so we proceed with our search for something which is less. So this is greater. Okay, we proceed, and here we found something that is less than this yellow bar here. So we have to have found something that can be swapped to the beginning of the array, and that's the whole point. Now we have something that can be swapped to the end of the array, and we have found something that can be swapped to the beginning of the array. So why not swapping them together? Yeah, and we do the check whether they haven't crossed. I and j haven't crossed yet, so then we do the exchange. We swap them. Here is the swap, and suddenly we have increased the improved the situation. Namely, that everything that is behind starts from here to the ith value. For those values, we know they are certainly less than the pivot. For those values, we know they are certainly greater than the pivot. And now we proceed. I is again looking for someone that is larger than this yellow line here, so we will stop here. Here we are, now it stops. And J is now looking for something which is less. It will stop here. Here we are, it stops. And since they have found values to swap, they will swap. Here we are, and we have swapped it. Now the situation is improved again. You see things behind this curtain are less than the yellow bar, and things behind that curtain are greater than the yellow bar. Okay, we proceed with our search. So here I has found something, now J has found something, they swap, here we are. And now they proceed with their search. I again is looking for something that is greater than the J value, so greater than the pivot value. So we'll stop here. Interestingly, it's something that it has already been examined. So NJ will stop its search because it has reached this situation. So that's the point. If I and J cross, and they will, then they will stop automatically, by construction. And what happens is that that we now don't do the exchange. We stop the inner loop because we have examined the whole yellow part of the whole yellow frame. And what happens next is that we put the pivot at the right position, and the right position is the position where I is pointing to it, because that is the position of the first element, starting looking from left, that is larger or than the pivot. So now we swap the pivot with this element here, and here we are. Suddenly this former pivot value has reached its final position. Everything that is before the pivot value is less than this value, and everything that's behind the pivot is greater or equal than the pivot. So we improve the array structure. And what happens next is we just return the position of the pivot. That's the purpose of the partitioning algorithm. Yeah. Okay. And if this partition happened, what we do next is we do again a recursive descent. Namely, we sort in the same style the array from L to m-1. So in this case, from here to here. So these are not sorted yet and will be sorted with the help of Quicksort. And if this is done, we sort this array, the other part of the array, starting from the pivot's position +1 to R. So from here to here. Yeah, so let's see how it works. So now we consider this. Remember, this is the previous pivot. And now we change the frame, so to say, and suddenly now this is the pivot. We have a different pivot now. We will partition everything now again with the help of this pivot, and you see easily that this is the only one which is larger than the pivot, and the other ones are less. So it's clear how it works. So we start with our search. I will looking for something which is greater, and we'll stop here. Now it stops, and J is looking for something which is less, so it will stop after one step. Here it is, and now they have found elements to swap, but they have crossed. So since they have crossed, they don't do the standard exchange, they just stop the inner loop because they have examined the whole array already. And then they know where to put the pivot by just one exchange. So now we know that this element, the former pivot, has reached its final position. This previous pivot has reached its final position, and we have this array that has to be sorted, and this small array that has to be sorted too. Okay, now we do recursive descent. This is a new pivot, and now we do the same trick again. We're looking for something that is greater. Okay, stop. We're looking for something that is less. Stop. Do the exchange. Here we are. And proceed with the search. I and J will search for something to swap. So you see I stops here and J stops too directly, and so they have crossed. So we just swap the pivot with this element here now. Here we are. And now we do the recursive descent to this part of the array, and we have a new pivot. There's not much to compare. That's interesting to see what happens now, because now we are running potentially out of bounds. So now I is looking for something that, so the I index is looking for something that is greater than the pivot. Well, when does it stop? It will stop if it reaches the pivot itself. Yeah, so then it will stop automatically, because the pivot is not less than the pivot itself. Yeah, so it stops automatically, and now we are looking for something which is less than the pivot, and we find it immediately. So here we are, and then we do this exchange. Interestingly, it is the exchange with itself, so nothing happens at all. And then we know that this has reached its final position, and then we do this quicksort on these two elements. We do the partition on two elements, very easy. So this is the pivot, this is the one to compare. There's not much to see, not much to do. We do one exchange and we are done. Okay, now we have achieved a lot of improvements here on this part of the array, and this one is more or less not sorted yet, but all elements are greater than this first pivot that we considered. Okay, so now we do the recursive extending for this poor array, but this is very easy because it only consists of one element, so there's nothing to do. So then we know that this is sorted now. Then we consider this element, this array, which has only size 1, so there's nothing to sort. So as a consequence, we know that this is sorted too, and now we know that this is sorted. So that was part of the recursive descent with some arrays which have just size 1. And now we proceed with this array of size 7, and we have this pivot. We do the standard partitioning algorithm now. So we set I and j to the appropriate values, and I is again looking for something that is greater than this pivot here. It finds something, and j is looking for something that's less. So that's more difficult. Here it has found something, and then the exchange, and proceed with their search. So I is looking for something that's greater. It's done. Now j is looking for something which is less. So it has to walk. Now it has found something, but it also has crossed the position of I, so we know that we have to change the pivot with this position here, and then we are done. So this has reached its final position. This is an array of size 1. We will see that this will be handled next. Okay, that's very easy to sort. And we will proceed with this part of the array, now consisting of 5 elements. Okay, and now we deal with this pivot again. Here we are, so this is the line. I is looking for something which is greater, so it stops here. Then j is looking for something which is less, so it will stop here. And you see, okay, it has crossed the, so we know, okay, we can change this with the pivot. Here we are. So then we have one array of size 1, which is very easy to sort. There's nothing to do. And here's array subarray left with array with size 3. Okay, now do the partition again. So this is the last element is almost the pivot. We search for elements to swap. There's not much to do, and then we do the final swap here, and then we are more or less done. So this is very simple to sort. This is very simple to sort. That means that we have sorted this subarray. That means we have sorted that subarray, and that means that we have sorted that subarray, and that means that we have sorted the whole array. Then we are done. So this is the array. This is the idea of Quicksort and how it works. It is a bit difficult to understand the construction of the pivot, and to understand why it sorts, but actually it's just picking one element to compare everything against this element gives you information. If you do, you get the information. Okay, these are the elements which are less, and these are the elements which are greater, and you put them just at the right places roughly, and then you proceed. And pick if we have a smaller set after the first comparison, you pick yet another element to compare with, so a new pivot, and you proceed recursively until you have reached arrays of size 1. So a similar approach than merge sort, but it is a little bit more difficult to find out what is a good pivot. And in order to get rid of silly cases, it does just the shuffle to ensure that the pivots that we choose, we always pick the one at the very end of the array to consider, is more or less a random value. Yeah, so of course it's possible that we have a bad luck and we just pick the minimum or the maximum or something like this, but in general, in the average, we won't do this. Yeah, so that's the idea of Quicksort.